Let's move on to talking about MatPlotLib in more depth. We touched on it briefly here when we talked about pandas by plotting this little bar chart here, but let's dive into some more depth with MatPlotLib. Let's go back to our Section 3 folder here in Jupyter Notebook. And I've already shown you a few times how to launch Jupyter Notebook by going to your Anaconda prompt and CDing into wherever you installed the course materials and typing in Jupyter Notebook. So I'm going to skip that step from now on, guys, okay? I assume you know how to do this at this point. So anyway, now that we're looking at Section 3, let's go into MatPlotLib13m and take a look at what MatPlotLib can do for you. So, some basic things you can do that you might want to do, especially in computer vision, is loading and displaying an image, right? So you can do that right with MatPlotLib, and we'll do that very often throughout this course. Again, we're going to start with $matplotlib inline. That just means we want to display the results from matplotlib as part of the notebook itself within our browser. Otherwise, it would open up new windows for all these images, and that would be kind of cumbersome. We start by importing the things we want. So we're going to import some specific packages within matplotlib, the image module, and we'll refer to that as mpimage. And we'll also import pyplot and refer to that as pltplot. All right, so let's start by loading up an image here. And since I actually started Jupyter within the appropriate working directory, we don't have to do anything here. We'll actually open this up in the right place. If you opened up Jupyter Notebook through some other means, however, you would have to specify a full path here to the actual file name. But for you, it should just work. So let's use mpimage.imread, image read, to actually import a JPEG image. And that's all there is to it. This is a color image, so we're going to call it image_color. And then to actually display that image, all we have to do is use the pyplot that we call plot, imshow, image show, with that resulting image file. So let's go ahead and shift enter, and it does indeed work. So really easy. To read the image, we used mpimage.imread. To display it, we used plot.imshow. Easy peasy. But matplotlib is usually used for graphing things and actually visualizing data. So let's talk about some more examples of that. Let's start with a scatter plot here. From Pylab, we're going to import the randn module here. That just gives us a very easy way of generating random numbers within a given range. So we're going to say x is going to be an array of random numbers, 100 random numbers, and randn means that they're normally distributed around 0 by default. So that's just going to give us a normal distribution around 0 in the x-axis and also 100 randomly distributed values on the y-axis as well. We can then say plot.scatter x comma y. So that's going to take each set of x and y coordinates and make a 2D point out of it. So the first element of x and y will form the point for the first point in our graph. The x1 and y1 will form the second point, and so on and so forth. We can also embellish our resulting scatter plot by putting a label on the x-axis called age. Let's just pretend that we're plotting normalized age values or something like that. Just an example to show you how to actually label an axis. And then we'll use the show command to actually display the resulting plot. And it does look like that. It's random, so every time it'll look different if you want to run it more than once. Kind of fun. But that's all there is to showing a scatter plot using matplotlib. Just scatter with your dimensional data, label any axis you want to label, and show it. That's all there is to it. What else can we do? Let's take a look at plotting a line graph here. So this defines the x values that we want to compute y values for that we're going to plot. So we're not actually plotting a function in its pure sense. We're actually sampling a function at 0.01 intervals along the x-axis between the range -3 to 3. So now we have this big x array that came out of NumPy that contains values at every 0.01 intervals between -3 and 3. So this is just a big old array from NumPy at this point of x values. We can then just call plot from pyplot on that x array, and for the y values, we're going to call the norm.pdf function. This comes from the scipy.stats function, and what that does is return a probability distribution function that is by default a normally distributed bell curve. So this is just going to take all of those x samples along the x-axis and plot that against the return of this function, which should give us back a nice little bell curve, show it, and sure enough, that's what we get. And you'll see a trick like that often with matplotlib in general. If we want to fill up a graph with sort of what looks like a smooth line or smooth contours, often what we're really doing is sampling that graph at distinct points and plotting those distinct points. We can also plot more than one thing at a time. So you can actually call plot multiple times on the same plot. For example, let's plot that huge array of x values against the original probability distribution function that's just centered around 0 by default. But we'll call it again against another normal distribution function, this one with a different mean and a different standard deviation. That'll be a little bit different. And by calling plot more than once, it's going to put both of those plots on the same plot. And then we can show the whole thing. And you can see here that we're actually plotting that original function along with the second one that has a different mean and different distribution. If you want to save these things to disk, you can do that too. We can take that same plot, take those same two functions, and save it off to a file, MatPlot.png, in whatever format you want, PNG format. Run that, and if you go back to our course materials, you should see that file now. Let's go back to our C drive where our materials are. Self-driving materials, we're in section 3. Sure enough, there's MatPlot.png. If I open that up, it contains my plot. So that's how you save it to disk, should you need to. We can also mess around with the look and feel of the resulting plot if you want to adjust how the axes look. Here's an example of that. So here we're setting explicit limits on the x and y axes. So we're saying we want to extract the axes themselves so we can mess around with them. That's what this plot.axes function does. And then once we have those axes, we can set the x limits from -5 to 5. So that means that our graph is now going to span from -5 to 5 instead of -3 to 3, which is actually the range of our x values. And we'll set the y limits of 0 to 1. You can see that here. We're ranging from 0 to 1 now. You can also set the ticks. So we're going to say explicitly we're going to have a set of tick marks on the x-axis at these values, -5, -4, -3, -2, and so forth. And the y ticks will be at this list, 0, 0.1, 0.2, so on and so forth. We'll then plot those same two functions and show it, and you'll see we have the same graph, just with the specific ranges and ticks that we specified for our axes. You can also add a grid to it if you want to. Same idea here. All we've done is say axes.grid to add in a grid to the resulting plot as well. The rest is the same as before. Go ahead and run that, and you can see that we do get a grid aligned with all the tick marks that we defined. So that's all you need to do to add a grid to your matplotlib graph. You can also mess around with the colors and the line types if you want to. All we're changing in this example are these two lines here. So our plot command, we've added some extra parameters here. This B- means that we want a blue line that's solid. That's what that minus sign indicates there, a solid line. And for the other plot, we're going to say R:. The R signifies red, and colon just signifies a dotted line. So, you know, the colon kind of looks like a dotted line. The dash kind of looks like a solid line. That's where that comes from. Show that, and sure enough, that's what you get. Nice solid blue line for that function, dotted red line for that function. You can also label these and add a legend if you want to. So we're going to add a little bit more to our example here. We're going to use X label and Y label to explicitly label those axes. We'll call them greebles and probability. And we'll actually say that these two lines signify sneeches and gacs. I'm totally making stuff up, of course, here. And the loc parameter indicates what corner or what position in the graph you want that to appear at. So we're saying we want to label the x-axis greebles, y probability, and we want a legend that says the first plot is for sneeches and the second is for gacs. And sure enough, it does work. Got a nice little legend here in the corner that says the blue line is sneeches, the dotted red line is gacs, and our labels show up accordingly. And if you really want to have some fun with it, you can even go all XKCD style. It's a popular web comic from, well, I think it's still popular. It's popular about 10 years ago anyway. Anyway, you probably recognize the style from the internet. You can actually say plot.xkcd, and that will automatically make everything look like a web comic for you. Just kind of a fun thing. And here's an example of what that looks like. So if you plot time over my overall health, you can see that your health was constant until the day you realized you could cook bacon whenever you wanted to, and then your health just went downhill from there on out. So just a little fun example. You can also do different types of charts, pie charts, for example. First, we need to remove XKCD mode with plot.rc defaults to go back into default mode. And then we can actually plot a pie chart here. So we have a list of values here, a list of colors that we want associated with those values. We're going to say that we're going to explode the blue one there, that third value, by 20%. Assign these labels to each pie segment. And then we just say plot.pie with all those parameters. So we say we want to plot this array of values using these colors and these labels and this information about which segments we want to explode out. We'll give it a title of student locations and show it. And there you have it. Sure enough, the blue Russia segment got exploded out 20% just like we wanted to, and everything else are the colors and labels and data that we specified. You can also do bar charts, pretty straightforward. We just have a list of values, colors that we want associated with each value if you want to specify those, red, green, blue, cyan, magenta. We will do a plot.bar to get a bar chart with the values ranging from 0 to 5, so that's going to be our x-axis values, and then the y values will be on the values. So basically we'll have 0, 1, 2, 3, 4 plotted against 12, 55, 4, 32, 14 with those colors that we specified. So there you have it. Again, bar, we're just saying the x values are range 0 to 5. The y values are coming from the values array that we have up here, the values list rather, and the colors are coming from this list of colors, and it does exactly what we told it to do. Let's look at another scatter plot here. We looked at one of these earlier actually, same idea. Just use plot.scatter for whatever x and y values you have and then show it. Easy peasy. Histograms, also easy to do. Histograms show how frequently each unique value within your data actually appears within a given range. So, for example, let's say we want to plot a histogram of incomes from some random distribution of people. We'll say we want 10,000 samples centered around $27,000 with a standard deviation of $15,000. So we generated some fake income data for a set of 10,000 fake people. We can then just easily say plot.hist with that income data. And we would say that we want it broken up into 50 different bucket sizes. So this gives us back a histogram of incomes broken down into 50 different percentiles, if you will. Then show it. There's what we get. So histograms, super easy. We can also do box and whisker plots. These are used for visualizing the spread and skew of data. So a little bit, if you're rusty on your statistics, you might need a little bit of a refresher of what box and whiskers indicate. Basically, it shows you the distribution of data. So the box represents half of the data where that exists. This line indicates the mean, and then these bars represent the outer quartiles of your data. Okay, the things that actually extend outside of those whiskers are outliers, things that are just really outside of the normal distribution of that data that you're feeding into it. So for an example here, let's take a uniform skewed set of random numbers. We'll throw in some outliers on the high end, some outliers on the low end, concatenate them all into a single array and just call a box plot on it and show it. So this is just taking a 1D array of data and letting you visualize what the distribution of that data looks like. So this is telling us that half of our data, the first two quartiles if you will, live within roughly plus or minus 30. The mean is a little bit above 0. The outermost quartiles extend to around plus or minus 100, 120 or so. And then we have all these outliers that we added in manually. And those just show up as individual data points, indicating that they are the outliers that they are, that you shouldn't really place too much faith into. All right, if you want a little bit of an activity here to practice what you've learned, try creating a scatter plot, just representing random data on age versus time spent watching TV. And label the axes just to make it look pretty. So you've had a couple of examples of scatter plots here. This should be really easy. It's just an opportunity for you to get a little bit of hands-on activity with Matplotlib before you start using it later on in the course. So give that a shot. Hopefully it's pretty easy, and then we'll move on to Seaborn, which is basically Matplotlib on steroids. It's fun stuff.